Is it clear? Class reps, all what I have said, is it clear to you?
Yes,
Any
sir.
Yes, sir.
questions?
Yes, sir.
Good.
Yes, sir.
So let's begin now. I have about 4 hours to spend uh, with you. So now, what is surveying, which is also called geomatics? Now, surveying is the arts, science, and technology of determining relative position of points above, on, or beneath the Earth's surface, or of establishing such points. So when we are determining the relative position of points on the Earth's surface, beneath the Earth's surface, or above the Earth's surface, so what we are simply doing is surveying. Okay. So a discipline which encompasses all methods for measuring, collecting information about the physical earth and our environment, processing that information, and disseminating a variety of resulting products to a wider range of clients. So in surveying, we are interested in determining relative position of points in three locations: on the surface of the earth, beneath the surface of the earth, or above the surface of the earth. On the surface of the earth, you are referring to our terrestrial ground, the ground you walk on, your topography, Then the beneath, when we are looking at the underground, surface, where we have mineral deposits, all right? Or maybe you want to do underground tunnel where train will move from point A to point B. So you need to carry out measurements. You need to determine relative position of points. And you will be doing that beneath the Earth's surface. All right. So surveying these with measurements. Measurements in surveying, we look at distances, we look at bearings, we look at angles, okay? And those are the things. We look at elevation or height or depth, So those are the various measurements we do in geomatics. As we proceed, we are going to look at all those types of measurements in details. All right. So geomatics, I've said that geomatics and surveying, is a word we use interchangeably, but geomatics now encompassing more broad aspects of surveying. In geomatics now, you are not just doing measurements. You are not just determining the relative position of points on the Earth's surface. Now, you are now also doing analysis. You are also doing data storage. You are doing data manipulation. Okay. So, and you are also doing data updation. All of this using advanced technology tools like your GIS. GIS is called Geographic Information System, and other advanced modern tools in interpretation of your data. And this data I'm referring to is the position of points on the Earth's surface, beneath the Earth's surface, or above the Earth's surface. So this position of points, in your mathematics, we call them coordinates. In 2 dimension is XY. In third dimension, we call it XYZ. In fourth dimension, we call it XYZ and T. Okay, so these are the parameters that define your position of points on the Earth's surface. So now, position of points. The points could be any object on the Earth's surface. Okay, but as far as this course is concerned, because we are just introducing surveying to you, we are going to limit our objects to land property. So it will be position of points defining boundary of land. Okay, so that's what we are going to limit this course. So as far as determining the relative position of points above or on or beneath the Earth's surface is concerned. Now, let me point out to you that aside land property, there are other objects that a surveyor or a geomatics engineer is interested in. I've told you earlier on about the mineral deposits. The objects could be gold. It could be, where can we find water beneath the Earth's surface? Maybe a town or a village need water. Okay, where can we get water? Okay, beneath the Earth's surface. So it's the job of a surveyor or a geomatics engineer to give a detailed mapping, which shows the location of where water is located beneath the Earth's surface, adopting different techniques in achieving that set goal. So the object could be in the telecommunication industry, where a company wants to site a telecommunication mast. Okay, let's take for instance Lagos States, where we have issues of network. You may call now and your airtime will be going and you won't be able to hear the person you are talking to. Either you can't hear the person or the person you are talking to cannot hear you, vice versa. So a case scenario whereby, okay, let's cite a telecommunication mast so that we won't have epileptic network, whereby callers can hear themselves without no interruption. So, and what they need to do is to now site telecommunication masts across Lagos cities. And this telecommunication mast cannot just be sited in any place they wish. They need to do a survey. Where are the proper position to site this telecommunication mast, so that everywhere will be covered across the city. So this deal with surveying, positioning of points, where and where to site these telecommunication masts. What is their position on the Earth's surface? And that is surveying. So it may be in a road construction where the civil engineer want to construct a road. Okay, the civil engineer needs to know the heights of points on the road. Okay, so that it can design the road in a proper way, such that maybe when there is rainfall, will not have coagulation of water on the surface of the road. When rain falls, the water will be able to flow, to the drainage at the left or at the right hand side. So for a civil engineer to do construct a standard road, he needs information about acts of points on the road, and that is surveying. That is surveying. So as I've said earlier on, that position of points is either in 2D or 3D or in your 4D. Okay. So there are various aspects, where we can deploy surveying. So the points, as I earlier said, could be anything on the surface of the earth, beneath the surface of the earth, or above the surface of the earth. It may be in the military. The points, the objects of concern may be my enemy. Okay, I want to shoot a missile from where I am to my enemy's camp. So how will I launch a missile such that it will get to the intended targets and not miss the targets? Okay, so I need positioning. I need to determine the position of where I'm sending the missile to, and that is surveying. So that is military application now. So we have various aspects of surveying application. We are going to also look at that. So as I said, that the position of points could be any objects on the earth surface. It could be a building, could be a telecommunication map, it could be a electric pole, anything you may think of. You want to determine the position of that object on the surface of the earth. And it can be in 2D, in 3D, or 4D. All right. So that is surveying. And also explain geomatics. Geomatics now is now a broader aspect of surveying, although most of the time we use it interchangeably. When we are saying surveying, we can also say geomatics. All right. So why is measuring and monitoring important? Okay. Why is measuring and monitoring important? Because in surveying, we don't just do measurements, we do monitoring. All right. Monitoring. Take for instance now, in surveying, we do what we call building, deformation of building. And what that entails is that we want to know if a building is undergoing or experiencing what we call subsidence. Subsidence, it may be vertical subsidence, it may be horizontal subsidence. Okay. And those kind of building where, we look at a ridge or a skyscraper building. How is it shifting in the horizontal or vertical axis? Okay. Or how is the building moving? So we're monitoring the deformation of building, and over time we were able to say that, okay, this building is moving in the X direction at this magnitude, in Y direction at this magnitude. So those are one of the aspects of monitoring as far as surveying is concerned. So reasons for measurement and monitoring. Why is it important in geomatics? Population expands, land value appreciates. When you have increase in population, all right, so that is one of the reasons why we do measurements and we do monitoring. Take for instance, I think Lagos State is about 20 million in population. Let's just take that figure, about 20 million in population. Now, That population, as at 1960, you know, I think, if I'm not mistaken, that population is not even up to 500,000. And look at uh, the landed property we have in uh, in Lagos States, you know, as at 1960, you know, and what we have now, you know. So the population, is increasing geometrically, and it can't even, the land available cannot even serve the need of this growing population. Okay. So you see a case scenario whereby people now begin to do sand filling, reclamation of land, like the Eco Atlantic city now is land reclamation, you know. So this location, what's it called, Lekki, used to be a swampy area. So everywhere was reclaimed, and people are now living uh, in all of those areas now, and more land are still being reclaimed, especially water bodies are now being samfilled, land are being reclaimed, so that we can have more land that will serve the growing population. So all of these have its pros and cons. And uh, in doing all of this, measurement needs to take place, monitoring also needs to take place, because you know there we have the merits and demerits of all of these activities going on. The same thing, land values appreciates, you know, land values. And one of the reasons why land values appreciate is construction activities in that location, okay? Or the location is now becoming an urban center, okay? Maybe where there's no road before, government comes in and begin to do road construction. What will happen in that geographic location is that the land value will appreciate. Maybe the land is being sold for 500,000, it will jump to times two of that price. Okay. And there will be need for measurements and monitoring, because people will buy land, you know, different economic activities will begin to occur in that location. Natural resources, uh, I think that should be dwindled. That's a mistake. Dwindle. Women's activities, that's a mistake. It should be human activities. Continue to stress the quality of our land, water, and air. I've mentioned that in my explanation. So those are some of the reasons why we'll uh, do measurements and we do monitoring in geomatics. Measuring and monitoring is possible in geomatics using modern ground area and satellite technologies. So computers for data processing, then contemporary surveyors. So in geomatics, measuring and monitoring is possible using modern technologies. We use area and satellite technologies. As I speak to you now, geomatics engineer or surveyor can use drone, to capture his data, and that is the area technology. And we have also satellites in space that can also be used to take acquire data and do measurements and monitoring on concerning the health surface. So, and we use computers for data processing. When we have a huge, large data, so computer comes in for us, to make our data processing more easy and efficient. Now, contemporary surveyors, no longer use tape, to measure their distance. They use advanced technology, to do that. Now, we have what we call International Federation of Surveyors, made following definition for surveying. Now, International Federation of Surveyors, this is an international organization, where surveyors all over the world are under one umbrella, and the name of that organization is called International Federation of Surveyors. And these are some of their definitions when they define um, the term surveying. Determination of the size and shape of the earth, okay, and measurement of all data needed to define the size, position, shape, and contour of any parts of the earth. Okay, so this definition has brought a lot of things together. You see that first, it said determination of the size and shape of the earth. So that's the first thing, to determine the size and shape of the earth, and measurements of all data needed to define the size, position, shape, and contour of any parts of the earth. So that's one definition of surveying. Now, another one says positioning of objects in space and positioning and monitoring of physical features, structures. I've mentioned structures the other time when I was talking about building deformation and engineering works on, above, or below the surface of the earth. All right. So, and these are, other definitions, at your leisure time, you can go through it. Of course, I will list this material to you. All right. So you see that when we are talking about surveying, is a, is a uh, is a is a profession that is broad. Now, geomatics now, the name is used for surveying in USA, Canada, United Kingdom, Australia. Surveying engineering is now called geomatics engineering. So let me quickly brush on this. What this slide or this session is telling you that when you go outside of Nigeria, in some countries, you won't see surveying, okay? The word surveying. So the word in USA now, Canada, United Kingdom, Australia, they use surveying, okay? And some countries, what they call surveying is geospatial science. They call it geospatial science. In some countries, you see them saying surveying engineering or geomatics engineering. In fact, the modern name now, is geomatics engineering. In some country or in some university, you see what they call it geodetic engineering. You see in some country geospatial science. Okay. So principal reason for name change. So let's look at the principal reason for name change. Recent technologies provided surveyors new tools for measuring and or collecting information, for computing, and for displaying and disseminating information. So one of the key reasons is that there's a recent technologies, that is driving the profession. Unlike in the 60s or 70s, when you call a surveyor to come and do measurement for you, maybe distance measurement, he or she will bring tape for you or a chain, okay? And nowadays, a surveyor does not need to stress his or herself to use chain or tape to do distance measurements. There are advanced technology, like electromagnetic distance measurements, device that can give you your distance in a twinkling of an eye for you. So that is one of the reasons why the name changed. Advancements in technology, increasing concern about the environment, locally, regional, and globally. And this has greatly exacerbated efforts in monitoring, managing, and regulating the use of our land, water, air, and other natural resources. Now, don't forget that surveying, we are not only dealing with lands, we deal with water bodies. Okay, water bodies. Anything on the surface of water and beneath the water surface, we do measurements and monitoring on that too. And in space, we are also interested in all of that. So let's move on. Field measurements for geodetic survey are usually performed to a higher order of accuracy than those of plane surveys. Geodetic surveying, the curved surface of the earth is considered by performing the computation. Okay, sorry. I think we have moved to the next one. So these are some of the reasons why the word surveying is now being changed, or is now changed to geomatics. One, as a result of advancements in technologies. And there's a wider view of application as far as surveying is concerned. Now, it's not just in environmental sciences where surveying can be deployed to solve environmental problems. Okay. Also in engineering applications, surveying or geomatics can be deployed. So that is why in some advanced countries, we have geomatics engineering. In fact, from inception, surveying and geoinformatics has been in the Faculty of Engineering at the University of Lagos since inception. So let's take notes of that. Now, there are two major classifications in surveying, and the two are geodetic and plane surveys. Geodetic and plane surveys. So when we say geodetic surveys, we are looking at, okay, let me ask us a question. The surface of the earth, is it straight or curvilinear? Can you hear me?
Yes, sir.
Can you all hear me?
Yes, sir.
Yes, sir. We can hear you, sir.
Yes, I'm asking a question now. I need your response. The surface of the earth, is it curved or plane?
Cold, sir.
Curve,
Hello?
sir.
So, okay, good. Is curved. Now, geodetic surveys, this with the curved surface of the earth. Okay. So by performing, we do computations on an ellipsoid. So geodetic surveying, we deal with the curvilinear surface of the earth. Everything is accepted to be curved as far as surface of the earth is concerned, which is the true reality, and that is the geodetic survey. All right. Now, let me ask this question this way. Can we assume that the surface of the earth is plane?
So that everyone would have stayed happy.
Can we assume?
Well, what are you saying?
I'm hearing an audio there. Who is that? Mute yourself, please.
Grandmother, don't talk nonsense, please. Why are you talking like Because when you I won't let you speak to me like that. I'm telling you
Once I
already.
find you out, I'm going to send you out of this class.
Just by being around.
Oh, Owolabi. So you are the one disturbing my class. Who is Badejo Place? Okorie Phillips. Mute yourself. Since you don't want to, I didn't say you should speak. So why do you unmute yourself? Mute the mic off your mic. Is when you want to speak that you unmute yourself and you speak. But as far as the class is concerned now, I'm the only one allowed to speak. Or you want to take my place, you want to come and lecture us, Badejo Place, Okorie Philip, Olaide Joy. You are wasting my time on Okorie Philip. Okay, I'll remove you now. So I'll remove Okorie Phillips now. This Badejo Place. You are out of my class. So I ask a question. Can we assume the surface of the earth is a plane surface? You've answered the question that the surface of the earth is curvilinear, is curved, is a curved surface. And I'm now asking, can we assume that the surface of the earth is flat, or is it a plane surface? Can we assume that the surface of the earth is flat or plane? Can we assume that?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, for those of you that say yes, why did you say yes? Oh, yeah, talk now. Michael Olamilekan.
Okay, so I want to say that because, like, from our perspective, we look at it from space, that's when we see that it is curved. But from us that we are on the ground, it is plain. So from our own perspective, we can assume that the earth is flat. But from outside space, people that are looking at it, they will see that it's curved.
Okay, you tried. Any other response or answers to that? Why is it acceptable to assume that the surface of the earth is curved? It's flat rather. All right, not to waste time. It is not when you are above the earth, as Olamilekan has said, that if you are in space, that is when you see the curves, the surface of the earth is actually curved. But when you are on ground, it is actually, no. It is not until you are outside the earth, you are in space. Now, when we are looking at a small geographical area, just look at where you stay now. Maybe you are in your at home or in an office, that space you are now, you can assume that the surface of the earth is flat. Why? Because it's a small geographical area, and all your assumption will be right. any measurements you do on that assumptions will be definitely accurate because you are dealing with a small geographical area or location. All right. But when you are dealing with a large geographical area, like the whole of Lagos now, maybe that's your geographical location, you can no longer assume that the edge surface is flat. Okay, because you are looking at a big expanse of land. Okay, but for a small geographical area, you can assume that the edge surface is flat, and you can do all your measurement and computation on that assumption, and whatever you have will be accurate. All right, and this is the classification, that is being done here. That we say we have two major or primary classification in surveying, which are the geodetic and plane survey. The geodetic aspect look at the curved surface of the earth in its entirety. When you are looking at a large area of land, definitely, you know that the earth surface is curvilinear in nature, and that is geodetic. But when you now have a small geographic area where you now assume that the edge surface is plane or flats. That is plane survey. We do plane survey there. But when we have a large geographical area, you cannot assume that the edge surface is plane or flat. It is now what? Curve. A curve surface. And that is what? A geodetic survey. In geodetic survey, we do a lot of computation on an ellipsoid. An ellipsoid is a reference surface, that takes the place of the size and figure of the earth. Let me ask you, what is the figure? What is the figure of the earth? The size and shape of the, what is it called? What is the shape of the earth? Eh?
Oblate spheroid.
Good. Oblate spheroid. Oblate spheroid. Now, what you are calling oblate spheroid is actually an ellipsoid. We have the oblate spheroid and we have the polate spheroid. And you are actually still referring to the ellipsoid. And the difference between the oblates and the polates is in their semi-minor and semi-major axes, which are the A and B. Okay, I don't know for those in geophysics if they are, you have actually, and I don't think you've even entered into your core course in geophysics. Okay, because a part, what you are doing in geophysics is what we call physical geodesy in geomatics, physical geodesy in geomatics. So when you say oblate spheroid, you are still referring to ellipsoid. I'm going to explain, give more details about that in a bit, but I want you to tell me the actual shape of the earth. Who is going to help us? Good, 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 good. Geode. I have seen about 3 responses now. Geode. Good. So the shape of the earth is geode. Is geode. Now, geode is an irregular surface of the earth. You can't model the geode. What do I mean by you can't model the geode? In a simple terms, you can't do computation on the geode. Why? Because it is an irregular shape. All right. So what the mathematicians did, these mathematicians now we call them the geodesists. Okay. What they did is now to adopt a shape that best approximates the geode. And that shape that best approximates the geode is ellipsoid. Okay. So why did they come up with a shape that best approximates the shape of the geode? Because geode as a shape, we can't do computation on it. We need to look for another shape that we can do computation on that shape, and it can also be taken, or an approximate shape of the geode, and that is the ellipsoid. I hope you get my explanation on that. So when you are saying the oblate spheroid, the polate spheroid, you are still talking about the ellipsoid. The ellipsoid is an approximate shape of the Earth, but the true shape of the Earth is the geode. So, but the geodesists now come up with an approximate shape, which is the ellipsoid, where you can do your computation. All right. Don't forget, I've told you that geode is an irregular surface, irregular shape. You can't do any computation on that shape. So ellipsoid, which is an approximate shape of the geode that best approximates the shape of the Earth, is now used so that we can do computation on it. So it is now becoming common to do geodetic computation in a three-dimensional Earth center Cartesian coordinates system. Geodetic methods to determine relative position of widely spaced monuments and to compute length and direction of long lines between them. So in geodetic survey, when we are dealing with distances, 1 kilometer distances, you know that distance cannot be a straight line again. It will have to be what? A curved line. Okay. In fact, any distances that is more than 250 meters, we don't take it as a straight line again, a curved line. So it is not advisable that I want to measure a distance and I drop my tape, and the distance I want to measure is over 250 meters, and I draw my tape from point A to B and take my measurements. That my measurement will not be correct. So I have to break it down, into series of measurements. So any measurement that is more than 250 meters is no longer a straight line. It is now curved. Okay. So I've told you for a plane survey, we are dealing with what? A small area of land. So we're also dealing in our measurements, we'll be dealing with what? Distances that are small magnitude. We can say 150 meter is still plane, 200 is still plane, but when it's now over 250 meter, it's no longer plane. So when it is above 250 meters now, and you want to do your measurements, we are dealing with geodetic survey. In fact, much focus is concentrated on any distances 1 kilometer and above. So take notes of all of this I've said. So I've explained the difference between geodetic and plane surveys, which are the two main or primary classification of surveying. Now, we have what we call GPS, Global Positioning System. Global Positioning System is owned by the United States of America. We have their satellites in space that give accurate positioning of any objects or points on the Earth's surface. Okay, I don't know if you've seen a GPS device before. Now, so these are still explanation on geodetic and plane surveys. All right. So don't let me. So importance of surveying now. What oldest and most important acts that is surveying for you? The result of today's surveys. What are the results of today's surveys? Map the Earth above and below sea level. Prepare navigation charts for use in the air, on land, and at sea. Establish property boundaries and private and public lands. I think this third one is what some of you are more familiar with. Survey that deal with landed property. Okay. How many of you have seen surveyors that are into landed property, boundaries of private and public lands? How many of you have had an encounter with such surveyors? Can you hear me?
We can. Yes, sir.
Okay. So establish property boundaries of private and public lands, develop data banks of land use and natural resources information, determine facts on the size, shape, gravity, and magnetic fields of the Earth. So this is how geophysics is related to us. Okay, prepare charts of our moon and planets. All right. So these are some of the importance of surveying. And in fact, this relevancies mentioned or highlighted there also speaks to area of application where surveying can be deployed, not necessary on land matters, as this course will focus on land matters. So there are other areas, as I mentioned earlier. So application of surveying. Surveying is used in the following sciences: agronomy, archaeology, astronomy, forestry, geography, geology. Can you see now? Geophysics. That's why you are doing this course, geology, geophysics students. Landscape, architecture, meteorology, paleontology, seismology, military, and civil engineering. Aside these sciences, there are other sciences that surveying can be deployed. All right. You know, in transportation, surveying can be deployed. Okay. Transportation, in security surveillance, surveying can be deployed. So there are wider application of surveying or geomatics. Okay. So specialized types of surveys. There are different specialized types of survey. We have control surveys. Control surveys entail establishment of a control framework across the geographical location. The geographical location can be a city or town, can be a nation or a country, as the case may be. Now, we have what is called datum. How many of you have heard the word datum? So I'm asking a question now. Datum.
Yes, sir.
So what is datum? D-A-T-U-M. What is datum?
Is it like a reference surface used to measure locations on Earth?
Is it what?
Like a reference surface that is used to measure locations on Earth.
That is,
Used to measure locations on Earth.
yes. Yes. Now, a datum, let me explain it this way so that you can get it. Let me go back to the ellipsoid that I explained the other time. You know, I told you that the shape of the Earth is geode, but geode is an irregular surface. So the geodesists came up with another shape that best approximates that shape, which is the ellipsoid. The ellipsoid is the mathematical surface of the Earth. That is what it is called, mathematical surface of the Earth that best approximates the geode. Now, for Nigeria, the region where we fall into, the portion of our geode, which is irregular surface, the reference ellipsoid that best approximates our portion of the geode is what is called Clark 1880. We call it Clark 1880. It's a reference ellipsoid, that best approximates the portion of the geode Nigeria falls under. So where we can do our own computation. I don't know if you are following me. So that's reference ellipsoid. That reference ellipsoid, we have is parameter, the semi-minor axis, the semi-major axis, the semi-minor axis, and we have the flattening. These are some of the parameters of a reference ellipsoid. Okay, we have what we call the first eccentricity, the second eccentricity. Those are the parameters that defines the shape of a reference ellipsoid, which helps in doing computations on the surface of the Earth. So for Nigeria now, we have a datum, and that datum is what I just explained now, the reference ellipsoid. What defines that datum is that reference ellipsoid. And what is a datum? A datum is a surface, a reference surface of the Earth, that defines positioning. Okay, there's a coordinate system of the datum that defines any position on the Earth surface. So that reference ellipsoid for Nigeria, which is Clark 1880, is our own datum. And what we call that datum most of the time is Mina datum. And that is what helps us to do positioning across Nigeria. Okay, all our points on the surface of the Earth within Nigeria is referenced to that datum, defined by the reference ellipsoid, Clark 1880. Is my explanation clear to you? Or I'm speaking in tongues?
No, sir.
Is all clear?
No, sir.
Okay.
Yes, sir.
So I'm expecting you as a university student not to just eat and digest all what I'm giving to you. You also go and explore, like the burial Jews. For those of you that are Christians, the burial Jews, they not only listen to what Apostle Paul is saying, they are fact-checking him. This man, what he's saying, is he actually saying the truth, or he's telling us lie? So that's what I expect you to do also. Don't just eat and digest what all I'm telling or I'm teaching you now. You also go and do your search, you fast check, you read further, and read more on what it is not clear to you. So we have control surveys. So control surveys now, we now have what we call controls. They are control framework established across the nation. So those controls, they are reference to that data, such that if I want to do mapping or surveying in Lagos State now, I don't have to go straight to where the datum is located to reference the points I want to establish in my vicinity. I have controls scattered all over the place that are already referenced to that datum. So I will pick the one closer to me to do my mapping or surveying work. I don't know if you are getting me. I'm still going to shed more light, give details on controls. Don't worry, we are just laying the foundation here now. So we have what we call topographic surveys. Topographic surveys, deals with knowing the terrain, elevation of points on a terrain, geographical area. So how high, how low a terrain is, topographic survey will give you that details, okay? And you'll be able to do any form of construction you want to do on that terrain. So in topographic survey, we have what we call contour map, okay? So the contour map give you information about how high or how low or how slopey a terrain is, okay? It's giving you height information about a geographical area. And doing a topographical survey help in engineering works like road construction, okay? Or you want to construct a bridge, on a terrestrial ground, topographic survey can provide elevation of points or height of points to civil engineers in constructing an accurate bridges or constructing good roads for public use. Then we have land. Yes, and I have said that this course will be limited to land matters, okay? Land, then boundary and cadastral surveys. All these ones, land, boundary, and cadastral surveys, still laying emphasis on land matters, okay? Survey done to define landed property, if you buy land now, you need to define the boundary, you need to produce what we call survey plan. So those are issues with land boundary and cadastral survey. So in generally, it is called cadastral survey. Now, hydrographic surveys, these are surveys done on water bodies. Okay, I've made mention of that earlier before, that we don't just do mapping or survey on the surface of water, beneath the water, the seabed. We do mapping of the seabed. Okay, there's a topographic fraction in hydrographic survey. We call it bathymetry survey. When you are doing the topographic survey of the seabed, we call it bathymetry survey. Route survey, that is when you are doing road construction, which will help the engineer in their road construction. We have the as-built surveys. As-built surveys, you are doing survey to confirm what is on the ground. Okay, you have a survey plan, that show details of what is on the ground. Then what is on the ground? Is it what is on the survey? So that is as-built plan. Let's say, for instance, I have a building at a particular location of interest, and my survey plan, that building, is it actually depicted on the survey? Okay, So you are, confirming what is on ground is actually what is on the survey that is produced. And when it is not there, you update it so that whatever the survey plan is saying is actually what is on the ground. So we are not just dealing with what is it called now, the boundary of the land now. We are actually also dealing with features on the land, e.g., building. If there is electric post on the land, you capture it. If there is a soccer way, you capture it. Any objects at all on the land, you capture it on the survey. So that is as-built survey, detailing and confirming what is on the survey plan is actually on the ground. And if it is not so, you rectify that. Mine survey, I've told you in when mining, miners looking for gold or silver, iron, or any other mineral resources. People don't just go underground and begin to mine. We must have a mining survey. Total station is one of the modern equipments or instruments rather that we use in geomatics. Oh, I thought someone requested that we should start recording before. Okay. Oh, I thought we were recording before.
Yes,
Hello?
I was recording. My network did somehow, so I had to start continuing.
Oh, okay. Okay. I've granted your request again. So we have the total station, electronic total station. So that's the picture you are seeing there. So you can see the total station is placed on a tripod stand. The tripod stand is that instrument that has 3 legs. It's called the tripod stand. Okay. Now, what is total station? Total station is an integration of your EDM, electromagnetic distance measurement, and your theodolite instruments. Now, what do we use EDM for? EDM is used for taking your distance measurements. Instead of using tape or chain, you can use EDM, electromagnetic distance measurements, to take your distance. Then you have the electronic theodolites, or theodolites as it is maybe called. So what is theodolite? Theodolite is for angular measurements. Okay, it's for angular measurement. Take note of that. Theodolite is for angular measurements. It's different from when I say it is used to measure angles. I did not say theodolite is used for measuring angles. I said theodolite is used for what? Angular measurements. The theodolite gives bearings or directions. Okay? It gives your bearings and directions. Then from your bearings and or direction, you can compute your angles. So that is why it is said that theodolite is used for angular measurement. So integration of your theodolite and your EDM, which is the electromagnetic distance measurement, combining together, integration of these two instruments it now becomes what? A total station. Becomes a total station where you can obtain coordinates of points, using your total station, you can obtain coordinates of points. If you set up on a known point now, then you can observe to the next point, and the next point you observe to, you can obtain your X and Y of that point you observe with the help of the EDM and electronic theodolites. So there's a mathematical model that has been programmed in the total station that when the theodolites captures the bearings for you, the EDM take your distances for you, Then the total station do the computation with the known coordinates set up, coordinates of points you set on. Then to the points you observe, it gives you the coordinates of the next points. I'm not sure if this point is clear to you, but I trust God that when we are able to hold a physical class, we'll have entered some aspects in this course that I will able to come back to this and explain this in details for you. All right. So, okay, there's an instrument mentioned earlier here also, the Global Positioning System, which is the GPS. This GPS is a satellite in space providing positional information on the Earth's surface. It gives you your XY of any points on the Earth's surface. Okay. So, which is the same purpose of which Todolite is also manufacture, or the purpose where we have total station. So if I'm not using total station, I can use my GPS. This is digital photogrammetric system. Wow. So this one is talking about another technique in obtaining positioning of points, relative position of points on the Earth's surface. So I don't want to go into that. Okay, so in photogrammetry, we use area images, and area images can be obtained using drones, using aircrafts, okay, mounted with sensor. So I don't want to go into that details, okay, because this is just introduction to surveying or geomatics. So we're just scratching the surface, okay. So safety, surveying safety. Can you see surveyors are also called geomatic engineers? Generally are involved in both field and office work. Now, for field work, they make measurements, observation using various type of instruments, as the case may be. And when they make use of these various instruments, they determine the relative location of points. They set up stakes in accordance with planned locations to guide building and construction operations. So that is for field work. Office work, research and analysis in preparing for surveys. Okay, computing and processing the data obtained from field measurements, preparing maps, plots, charts, reports, and other documents. So these are the things surveyors or geomatics engineers do on the field and in the office. So possible danger sources. No, in all profession, of course, there are hazards. Okay. There's no profession that will say, there are no possible danger, in their profession. So in city and artificial structure field measurement, noise, poor visibility, dust, sunshine, skin cancer, sunburns, heat stroke. Most of the time surveyor is under the sun, and all of these things that I mentioned now can be of danger to surveyors or the geomatic engineers. So for protection, surveyors wear safety vests, fluorescent orange color, flagging materials. Someone is calling me. Who are... Hello? Sorry, just give me a second. Now, the vertical distances are, what are referred to elevation, heights, or depths. depending on the nature of the projects the surveyor is doing. The surveyor is doing. So these are the 5 kinds of measurements. Now we have the units of measurements. When we are dealing with distance, you know that the standard units of measurements as far as distance is concerned is meters. Okay, for area, meter square; for volume, meter cube; for angle in surveying, we use what we call degree, minutes, and seconds. Degree, minutes, and seconds. Okay. So we can convert the degree, minutes, and seconds to decimal degrees or decimal or degree minutes, depending on how we want to move. So for most of the time, surveyors use degree, minutes, and seconds to represent their angles and bearings. Okay. Let me even ask us this question. What is the difference between angles and bearings? Who can help us? When you say angle and bearing, what is the difference?
Good morning, sir.
Yeah, good morning.
So I just want to try. I'm not really sure, but I
Please go
feel like
ahead.
angle is okay. Angle is a particular place, while bearing is how you get to that particular place, like the directions you take to that particular place.
Okay, you try. Any other response? Let's respond now. So it's only one person that can try. Oh, someone is saying bearing is the distance and one angle is the direction. No, no, no. That is wrong.
Sound to try.
Please go ahead.
So I think angle measures rotation between two lines or two distances, and bearing gives us direction from a point.
Bearing gives us direction to a point, but
From a point,
angles
measure rotation between two
measure
lines or rotation.
rotation between 2 lines. Okay, I get what you tried. Now, not to dwell much on this. Now, when we talk about bearing, uh, bearing is always to a reference line. When you say bearing, it's actually to a reference line. In fact, there's a topic that we'll do as far as this course is concerned. We're going to talk more on bearing. So bearing is always to a reference line. And the reference line, in geomatics, we have some reference line. One of the reference line is what we call the true north, or the geographic north pole. We can call it the true north or the geographic north pole. Now, another reference line is called the magnetic north. The magnetic north. In fact, we are still all of what I'm saying now, we are still going to discuss this in details when we are considering what we call compass surveying. We are going to, trash all of this in details. So bearing is reference to a reference line, and the reference line could be a true north or the geographic north pole or the magnetic north. So based on the reference line a bearing is reference to, we determine the type of bearing. For instance, if a bearing is reference to a true north, we call that bearing true bearing. When a bearing is referenced to a magnetic knot, we say that bearing is magnetic bearing. So can you see bearing now? But an angle, as one of you have said, you know, uh, angles between two lines is angles between two lines. If I have uh, uh, I stand on a point now, I'm on a particular point, and I observe to if I stand on a point A and I observe to point B, and I also observe
You
to
know they want to speak to us.
point C.
How do I get
So I
invited
have
as
two
a
lines
big
now,
lecturer?
isn't it? Line
He's a new
A to
lecturer.
B
Like the next.
and line A to C. Are you following me?
Yes,
Hello?
sir.
Yes. So the angle is between that two lines, which sometimes in mathematics we call it the observed angles or the included angles. Angle. The observed angle or the included angle. So that is angle for you. But the angle, if you take cognizance of what I'm explaining now, is obtained from where? The angle is obtained from where? Oh yeah, let's talk now. For my explanation now, the angles, the angle, that included angle of the observed angle between those 2 points is obtained from where? How did I get or obtain that angle? Angle between line AB and line AC. How did I obtain that angle? Or how will I obtain it? Let's talk now. Hello? I don't know why some of us cannot talk. You are not in the physical class. You cannot, So someone has said from the bearing, of course. That is correct from the bearing, but learn how to talk. It's not every time I'll be going to check your shots.
Yes, sir.
So from the bearing between AB and AC will give you the observed angle. Okay, so can you see the relationship between a bearing and a angle now?
Yes,
Okay.
sir.
Now, another thing about bearing and angle is this. Now, a bearing in itself, is an angle. Are you following me? A bearing in itself is an angle. In fact, let me put it this way. All bearings are angles. All bearings are what? Angles. But not all angles are bearings.
Okay, sir.
Okay. So I think I'll give more information about bearings and angles. So let's go back. So in angles or bearings, now we surveyors or geomatics engineers use degree, minutes, and seconds as units. And you can convert from degree to minutes, degree to seconds, or vice versa, how you want to do your conversion. So 1 degree equals to 60 minutes, and 1 minute equals to 60 seconds. Can you still hear me? Can you still hear me?
Yes, sir.
Yes, sir.
Yes, sir, we can.
Just hold on. I'm using an AirPod. So the battery just ran down. I'm on speaker now. So let me switch to another one. Just hold on. I'm trying to. Oh, can you hear me now?
Yes, sir.
Hello.
Yes.
All right. All right. So 1 degree equals to 60 minutes. 1 minute uh, equals to 60 seconds. So from this information, you can do your conversion from degree minutes, seconds to decimal degree, and vice versa. All right. So I hope that is clear. So if you are given 30 minutes, 30 degrees, sorry, 30 degree, 15 minutes, 30 seconds, then convert to decimal degrees. You should be able to do that. And if you are given decimal degrees, let's say 30.456 degree, convert to degree minutes seconds, you should be able to do that conversion. All right. So we're not in the physical class now where I can be given details and doing series of examples on that. So, any information about your hostel accommodation? What's the updates? Hello, because will be a factor if physical
Yes, sir.
class is going
So some people
to
have
come
given,
sooner or later.
some people have been given accommodation, and I think the moving date is on Saturday, but not everybody got,
Oh,
and every other person is still trying to resolve their accommodation.
all right. So hopefully we can start physical class next week. So class, we have look at the timetable. Where is the, what day? I think it's Tuesday. I'm not sure. Confirm that. What day the class falls on? Then uh the class, for the lecture. So let's move on. We have theory of errors in observation. Now, errors are important to surveyors or geomatics engineers, because I've just shown you 5 kinds of measurements where we listed them. As professionals, we are humans. So we are bound to make errors, or we are bound to incur errors in our measurements or observation. Okay? So the important thing is that how do we minimize this error? Or how do we remove or eliminate this error so that our measurement can be useful, and can be accurate and precise, you know, in various application, so we want to use it for. So good measurement require a combination of human skill and mechanical equipment applied with the utmost judgment. So good measurement is a combination of the observer skill and the how good the instruments or equipment the observer is using. So observations are never exact and therefore contain always errors. So any observation cannot be exact, even no matter how skillful an observer is, and no matter how accurate the equipment or instruments being used, you know, the measurement or observation cannot be free from errors. So what we do in surveying or geomatics is to reduce uh, the error to the barest minimum, okay, such that it has no significance in our measurements or observation. So surveyor must understand different kinds of errors, their sources, uh, expecting magnitude, expecting magnitude under varying conditions, and their manner of propagation. So since there are errors in our measurements, so we must understand the sources of this error. Where are they coming from? Okay, what is their origin? The types, their types, and how they propagate themselves in measurements. So having the understanding of what I just mentioned now will help us to deal with them in the uh, in the accurate way, in terms of removing them completely or minimizing them, to the barest minimum, reducing them to the barest minimum. So, as far as we are concerned, you can't eliminate the errors. No matter errors you will remove, there are still some errors that will still be there in your measurements. So, what we can do is to now make sure that it is of no significance, as I've said earlier on. So that type of errors is random errors. Those ones, they are always in your observation. So what we do to them is to make them insignificant in the measurements. Okay. So surveyor must be capable of assessing the magnitudes of error so their acceptability can be verified, or if necessary, new ones are made. So we have direct and indirect observations. So let's look at examples of direct observations. Applying a tape to a line, fitting a protractor to an angle, turning an angle with a total station instrument. So these are some examples of direct observations. All right. Now, indirect observations. Indirect observation. Observation are determined by its relationships to some other value or values. Now, example, the distance across a river can be found by observing the length of a line on one side, the angle at each end of this line to a point on the other side, and then computing the distance by one of the standard trigonometry formulas. I hope that is uh, uh, taken. That is uh, well understood. Direct observation, indirect observation. I don't want to tell more stories about that. If I want to mention line A and B, I can just drop my tape, maybe a distance of 10 or 20 meters. So that's direct observation. But if I don't have access to that line A to B, I can't draw my tape from the one end of the line to the other end. Okay, no access. Maybe there's a danger. I can't access the place. So I can do measurements in another parts around, and use my trigonometric ratio, to do computation as explained in the indirect observations. So I hope that is clear. So errors in measurements. Errors in measurement. An error is the difference between an observed value for a quantity and its true value. Okay, it is unconditionally stated that no observation is exact. Take note of that. No observation is exact. Two, every observation contains error. I've mentioned that before. The true value of an observation is never known, and therefore the exact error present is always unknown. So let me quickly summarize all of this. An error is the difference between an observed value for a quantity and its true value. Okay. Now let me use line A to B. 2 points define a line A to B. Now, if I know the true length of that line, let's say the true length is 40 meters. I'm just assuming now. And my own observation says the length of the line is 30.5 meters. So the error in my measurement will be what? 40 minus 30.5 meters. So that is what that expression is explaining to us. That the difference between the observed value and the true value of a quantity the is called error. The difference between the observed value of a quantity and its true value is called an error. Now, we have said that there is not exact measurements or exact observation. You can't have exact value of a quantity. That is, you do not know the true value of any measurement. For the distance A to B I mentioned now, nobody can give us the true length of line AB. No one, okay, except God. So as long as we are human, we can't give, there's no true length of line AB. All right. So every observation then we have error. Every observation, has error because there's no true length of or observation of a quantity. So the exact error present is always unknown. So which means since I can't have I don't know the true length of a quantity, therefore I can't know the error. I hope what I'm saying is making sense to us. Is it clear? Let's respond.
Yes, sir.
Since I don't know the true length of a quantity, there's no way I can know the error. All right. But from our definition, it is said that an error is the difference between the uh, observed length of a quantity, and the true length of that quantity. All right. So let's move forward. So then, what do we actually call error? Then, if we don't know error, if we don't know the error of a particular quantity, of a particular measurement, since we don't know the true length, then what do we call the error? Most of the measurements or the quantity that we call error is actually what is referred to as residual. Residual. The residual is the difference between the observed quantity, the observed length of a quantity, and its most probable value. So, since we don't know the true length of a quantity, what is known is the most probable value. The value we think is the true value. That is what we call most probable value. That is a value that is close to the true value. So when we now do our own observation to get the error, we now say the difference between the most probable value and the observed value is the error. But that error is now called what? The residual. Since we don't actually know the error of a particular quantity. I hope my explanation is clear. Hello?
Yes, sir.
All right.
Yes, sir.
Yes, sir.
So we have
Yes, sir.
what we call mistakes. Mistakes. These are observer blunders. When an observer causes blunders while taking observation on the field. What are some of the things that result to blunders? One, misunderstanding the problem. When the problem is not understood, blunders are inevitable. Carelessness. When the observer is careless, blunders will always occur. Fatigue. When the observer is tired or stressed, blunders will definitely occur. Miscommunication. Miscommunication. You know, when you are on the field or on the site, we have the observer and the what we most refers what we refers to as a booker. The observer cannot be the booker at the same time. That is the one recording the observation. So we have another person recording what the observer observed on the field. So if the observer observed a distance of 40.56 and the booker now record 40.65, so that is a blunder. So in that observation. So poor judgments also. So these are some of the reason why we have blunders or mistake. Another name for this mistake is gross error. We call it gross errors. Instead of saying mistakes sometimes, we call it gross errors. So take note of that. So this also is given details about the mistakes. So sources of errors. Now let's look at sources of errors. Natural errors. And how are they caused? Caused by variation in wind, temperature, humidity, atmospheric pressure, atmospheric refraction, gravity, and magnetic declination. Okay, so when all of these are responsible for errors, uh, these errors are called natural errors. Okay, wind, temperature, humidity, atmospheric pressure, atmospheric refraction, gravity, and magnetic declination. Now we have instrumental errors. Imperfection in the construction or adjustments of instruments and movements of their individual parts. So when an instrument is not well constructed or adjusted, that is when we have instrument error. Or the instrument may be well perfected, constructed, adjusted, but the way the observer is moving the parts or is handling the parts of the instrument while taking observation can lead to instrumental errors. So the third one is personal errors. Arise from limitation of woman's sense, sight, and touch. Okay, so that is personal errors, woman's senses. If someone the observer is having issue with his sight, maybe he has long-sightedness or short-sightedness, that could lead to personal errors. Okay, and also touch, sense of touch. Okay, so personal errors. So I've mentioned and described to us three sources of errors in observation: natural errors, instrumental errors, and personal errors. Let's take notes of that. Now, we now have types of errors. Types of errors, which are they are different from this. So, okay, so let's look at systematic error. This error occur according to a system. It follows a defined pattern. So the error occurs according to a system and it follows a definite pattern. Thus, if an experiment is repeated under the same condition, same pattern of system errors will occur. These errors are dependent on the observer, the instrument used, and on the physical environment of the experiments. So the error depends on the observer, the instrument, and the physical environment of the experiment. Any change in one or more of the elements of the system will cause a change in the character of the systematic error. depending the one driving those mathematical models. Take for instance, when Archie establish his laws, which law of Newton should I use now? Okay, let me use his gravitational law. Okay, so his gravitational law, is a physical law, and that law is governed by a mathematical equation. Okay, so the same thing with a systematic error. They obey a physical law, and the physical law is explained by mathematical model, mathematical formula that establish relationship between parameters in the physical law. So don't forget, the systematic error is a function of the observer, the instruments the observer is using, and the environment where the observation is being taken. So let's take notes of that. Then random errors. After mistakes are eliminated and systematic errors are corrected, a survey measurement is associated with random error only. So what are we saying? When all errors are removed, the gross error, systematic errors are removed. The only errors that will be left is the random errors. So this error is small and is equally liable to be plus or minus, those partly compensating in nature. Random errors are unpredictable and they cannot be evaluated or quantified exactly. So that is the error I was referring to some minutes ago, that no matter how you try to remove error, there's this error that will still be there, which are the random errors. So we can only minimize them to the barest, reduce them to the barest minimum. All right. So that is errors for. So don't forget, we are looking at theories of errors in observation. Now, what is precision and what is accuracy? I know it's a common word that this thing is not accurate. This thing is not precise. So who can help us with that term? What do you understand by accuracy and what do you understand by precision? Let's talk now.
So accuracy is the closeness to how true the value is, and
Accuracy is what?
is closeness to the true value.
Accuracy is the closeness to the
True
true
value.
value. Okay.
And precision
Precision.
is consistency of repeated results.
Okay. Consistency in what?
Consistency of repeated results
Okay.
of the
So,
accuracy.
okay. Can you see the diagram I'm showing now on precision and accuracy? So when we talk about accuracy, we are talking about the degree of closeness or nearness of a mentioned quantity to its true value, okay, or to its most probable value, okay. Don't let me use the true value now because we don't always have the true value. So the degree of closeness or nearness of a mentioned quantity to its most probable value. So that is accuracy. But when we have precision, is consistency in a set of observations. You are having a consistency in a set of observations. Now, that's consistency in a set of observation is called precision. Okay, so which means from that definition or the explanation I gave now, when we say a value is precise, it does not mean it is what? It is accurate. Abi? A value can be precise, but it may not be what? Accurate. Are you following?
Yes, sir.
Yes, sir.
Okay. Now, this illustration will give you more insight. So, what we are trying to explain, accuracy and precision. Let's look at diagram C. Can you see the diagram? Hello?
Yes, sir. Yes, sir.
Now, diagram C, what is it saying? What is it saying?
Results are both accurate and precise.
It's not?
Results are both accurate and precise.
Yes, it's both accurate and precise. Can you see? There is consistency, and all the points are within the same space. They are close to one another. Don't forget, I said accuracy is what? Degree of closeness or nearest of a measurement to its most probable value. Okay, measurement of a quantity to its most probable value. So, and that is what is happening in figure C. Then aside that, we now have consistency in the sets of observation. All right. So diagram B now, what is happening here? This is not accurate and it's not precise. This is not accurate and it's not what? Precise. This A now, figure A is what? It is precise, but it is not what? Accurate. So I think that is all. We've exhausted this slide. Okay, so I think we spent 2 hours for this slide now. So I think although I intend to use 4 hours, my voice is, I have a dry throat now. And I'm not even on campus. I need to rush down to campus now. So today is Thursday. Class rep, can we have another class tomorrow?
Sir,
Is
by
that
what time?
possible?
By what time, sir?
Around this time, 10 to 12.
Yeah,
We have a class by 10.
when?
Okay. When is your class finishing? Eh?
Sir, by 12 we should be done.
Okay, let's fix 12 then.
Okay, sir.
All right then. So let's call it a day today. We meet by 12 p.m. tomorrow online. Class rep, you need to see me with your attendance so that I can sign on your attendance.